Okay, so hopefully everybody had a wonderful break and is ready to finish the semester strong. Because we pretty much have, I think it's 5 weeks of classes to go. And a week of finals, right? So you're definitely in the home stretch. And what that means is if you're in the home stretch, don't give up yet, right? Don't put it on autopilot. You want to make sure that you continue to work hard because, this stuff, we're still presenting material. And yes, we do slow down in the presentation of material as, people get full, and we understand that. But, make sure you put the time in because this is the important stuff. So, last class before break, we got into steady state errors, and we showed you how to calculate the steady state error. Just generically as ESS, we use the final value theorem. So you can find ESS, which is a time domain result, by using a Laplace domain result, which is doing the limit as s approaches 0, s E of s. Down here. And then we defined or discussed the concept of the number of poles at s equal to 0 was the number of integrators into our system. So if we have any poles at s equals 0, that means we have at least one integrator. And integrators, as you recall, they always try to integrate what the error is. And as long as the error isn't changing so fast, you're actually able to use your integrators to catch up. Well, changing so fast means that the input would be changing really fast. So the harder your input signal is to copy or follow, the more integrators you need to be able to do it. You basically speed up the system. We did the step input, which is, if we looked at, let me minimize this. We did our step input, which is a unit step. We would solve for k sub p, which is the position constant. And we can solve for k sub p by taking the limit as s approaches 0, gc times gp. And if it's a type 0 system, which means it has no integrators, then our steady state error was going to be a non-zero number. If it has one integrator or if it has a type 1 system, then we see that our proportional or position error goes to infinity, which means our steady state error goes to 0. Then we did a ramp input. So a ramp input for a system, if it's a type 0 or a type 1 system, we see that our position constant is no longer enough because we're trying to keep up with something that's ramping up. So I don't know who came up with the term position or velocity, but they are there. So we'll just stick with them. That's a consistent one. So our velocity constant is what we use when we have a ramp input. And we solve for that by multiplying our GC, GP, multiply it by S, and take the limit as S approaches 0. So with a type 0 system, we have a steady state error of infinity. Our ramp input is too fast for our system to keep up with no integrators. With a single integrator, it's not able to keep up perfectly, meaning it zeroes out the steady state error. So we have a little bit of error, and now we calculate it with whatever the constant is of your numerator, so whatever constant that ends up being, divided by your velocity constant. If it's a type 2 system, then our steady state error goes to 0. So this is all new starting today. So a parabolic, and again, in the real world, do these exist? I don't know. I'm not a control systems expert. I haven't seen a ton of them. The most of the systems that I've ever seen are actually going to be step input, but there are maybe some unique cases. If you get more and more into the controls world, where you're doing things with robotics, perhaps, like if you're trying to track something moving in the sky, like if you're part of air defense, then that would be something that might be a ramp input, right? Because you're tracking its position, it's rotating, so its position is changing relative to time. So that's not a fixed input. That's at the length of something is increasing. So that would be a case where perhaps you have a ramp input. Parabolic, I've never seen it. I can't even think of a practical term, but we cover it here because it's in your FE review manual. The table that we'll be presenting very soon, if you look at your FE review manual, that table actually exists in your FE review manual. And so if you know how to use these steady state error stuff, it actually makes things quite a bit easier. So my parabolic input, we have a ramp input. that, or sorry, not a ramp input, an input that has a t squared, right? Because that's the ramp. We convert that into the Laplace domain and we have a over s cubed. A just means it's whatever magnitude value it is. It doesn't have to be unity. It can be whatever value you want. Now we do our calculation for ESS using the formula that we developed at the beginning of last class. And we run that through, and what we end up with, once we get rid of our S term here in the numerator, by canceling one of those out, we end up with, actually we cancel it out over here, sorry. Cancel one of those out. What we end up with is an S squared plus S squared times GCGP. Now, we pretty quickly should know that this term goes to 0 when we take a limit function, because S squared, when S approaches 0, it's just going to get to 0 faster than S. So what we're left with is only this term right here. Because the GC and the GP could have an S squared here in the denominator, which would cancel out the S squared that we would have in the numerator. So it's possible that it can actually cancel out. So that's why we can't definitively say, well, we're multiplying something by 0, so it's going to go to 0. No, that S squared in the numerator can get canceled out. So we're going to define that as K sub A. Since we're multiplying by the S squared, that is the second derivative in the time domain of whatever we're trying to calculate. So first derivative of position is velocity. Second derivative of position or first derivative of velocity is acceleration. So that's why we call it the acceleration constant or acceleration error constant. And then if the system type is 1 or less, then we know that our K sub A is going to be 0 because the S squared term here is not going to get canceled out. And then when we calculate our ESS, we're going to end up with an infinite steady state error. We're unable to keep up. Not going to get there from here. Okay. So if it's a type 2 system, then we've got a chance because we see that those have the possibility of canceling each other out. S squared cancels out. So now we're going to end up with a non-zero number or a non-infinity number. So for type 2 systems, you can just go ahead and calculate what K sub A is. If it's a type 3 system, you know that that S cubed or greater that is going to exist here is going to cancel out all of those. And then that means that as that S cubed or beyond term approaches infinity, or 0, I should say, K sub A is going to approach infinity. So my steady state error goes to 0. All right. So this has or needs tons of integrators. It needs 3 separate integrators to be able to keep up with a parabolic input. So for type 3 or better, we can go ahead and do this. So how do you get rid of error? You just modify your controller. You can't modify your plant because you're not going to, I mean, you could modify your plant, but the reason why we don't modify the plant is because the plant is built to do some sort of process. It's trying to build something. It's trying to make a certain amount of water. It's built with tanks and pipes and all these different things to do something practical. So that's hard to change because, I mean, it's a physical thing. Where the controller is a PLC that you can go across the way and get that in the lab. So you modify your controller to go ahead and do that. So you have a more sophisticated controller. In industrial process control, we only have PID controllers. Okay. You can get into robotics, which have much more sophisticated one. You can use fuzzy logic, neural nets, that type of stuff. Do you know why they get more sophisticated controllers in the robotics and in those typical realms as opposed to in process control? It's not an obvious answer, but does anybody know what fuzzy logic or neural networks are? So it's fuzzy logic is, it could be like the temperature in this room. It could dictate if the thermostat is telling the heat to come on this room or not. So it's fuzzy, right? If you're in this band, it could be not on or it could be on. You need additional information. So fuzzy logic you have these overlapping zones that over here, the decision is less obvious. That's why it's fuzzy. So then a neural net is another way of saying AI, right? You basically have some, not AI, I shouldn't say, it's a deep learning or learning. So the machine does 10,000 or 50,000 samples, and it ends up coming up with a result that works. And so it actually just runs that through a computer application and spits out, well, based on these parameters, the output should be this. So these type of systems work for nonlinear systems, right? If it's a linear system, then why not just go with PID controls? But in more sophisticated controls, you need more nonlinear controls, so you implement that. In the real world, every system is nonlinear, but remember, our friends in the process control industry, their brains hurt enough trying to figure out how to keep these processes running. So what they try to do is they try to linearize the operation of the system. So even today, if you were to go to any industrial plant, you'll still see PID control. Again, it's just robotics and more sophisticated stuff. Maybe with cars today, like anybody know how cruise control works? They use radar, right? If you ever looked at the bumpers on cars, if you look and see those little circles in your bumpers, they're not there for looks. I mean, they kind of break up the line of the bumper, but the idea is that there's a radar, and then that feeds back in to the computer, and then you have something called adaptive cruise control. So it'll adjust the speed of the car based on how quickly you're approaching a car and a bunch of different factors. And so that's using more nonlinear adaptive control. What's interesting about that in our car, though, is everybody, oh yeah, let's get the latest and greatest technology, right? Sounds like a great idea. Anybody here realize or understand how often you get system updates for your car? Unless it's a Tesla. You never do. You might bring it to the shop and they might do some updates on it, but the reality of it is that, you know, if your car is a certain vintage, if you want to get system updates, you got to pay for that yourself. And so newer applications, what you're seeing is they will continue to update the software, but you have to pay a monthly subscription so that you get software updates. So vehicles, because of the increases in technology, even though your car, like let's say you go out and buy an M4, right? Like Barzilai will make Barzilai happy. He bought a 2024 M4. He's graduating next year, so 2025. Let's give him a year. Let's make him buy it today. The concept is that his car will be completely loaded and tripped out. But it might not be that he actually has all those functions enabled, because BMW is doing a subscription service that says, well, today you can have power seats and heated seats because you're paying the subscription, but next month you don't have access to that. And so car companies are investigating if they can do that as an option for them to make more money. So for $8 a month, you can get heated seats, or you can get adaptive cruise, or you can do whatever you want to do. BMW is actually one of the leaders in trying to do all this subscription stuff to see if people are willing to pay, because when you buy a car, it has all those bells and whistles built into it, right? You can't get heated seats unless the car comes with heating elements inside of it. So I purchased a car that already has that. So why can't I use it? Well, BMW says, well, we made it cheap. We sold it for you cheaper under the premise that we would get some subscriptions for it. So that's the way that they can make a profit. So that's the way that they're justifying it to regulators to say that it's okay. But that's happening more and more. And why are people buying new cars today? It's not because they have vast improvements over design. It's because of technology. Your BMW 2025 has an 8-inch screen, but that 2026 is going to have a 10-inch screen that's going to wrap around and have better graphics and yada, yada, yada. Yeah, well, people, that's the reason why people update, is because of technology. So if you go buy a car today, it seems absurd, but they just talk about all the bells and whistles in terms of technology. Is it a better car than the one 2 years ago? Probably not. It just seems like it because they're investing more in technology. You do the same thing, right? Who replaces their iPhone or smartphone every year? Be honest. How about every 2 years? Okay. Why do you replace it? More bells and whistles? It's not because your old phone is dead. Yeah, most people go every 3 years. Why? Because that's what your cell phone provider contract is. So you buy your cell phone and you replace it every 3 years because you get a new one for free, right? Is it actually free? It isn't. But so here's the thing, this is completely independent from this material, but if you want to be smart, you're better off to get the next Google phone, I think the Pixel 8, because one of the things in your cell phones, and this happened to me because I had a 5 or 6 year old cell phone, I had an OS that was from like, 5 years ago. And so there were some apps that wasn't running properly because they wouldn't work with such old operating system on the phone. But the Google Pixel, they promised to keep updating it so that it would receive OS updates through 2020. It's the only phone that they've guaranteed that it'll be through 2020. That's the Pixel 8. So if you're looking for a phone that you don't want to have be obsolete because of the OS, then you might want to be smart about your phone. I don't know how iPhone does it, but Android phones are really notorious for if you have to scrap them in a couple of years because their OS has gone backwards. So useless information. All right, one last thing before we start looking at examples. Why are we keep saying this is unity feedback? Doesn't need to be. We can certainly put an H down here, right? There's one reason. It's kind of silly, but it is a reason. If you want to compare your input to your output, don't they basically have to be the same quote unquote signal type? If I want this to be RPM, this input had also better be RPM, right? Because you can't get an error between the two. If this is input is, let's say it's 2 volts, correct? How would you compare 2 volts to 1800 RPM? Doesn't really work. So normally what you do is you want those signals to be the same. That's why you'd say unity feedback. But there's nothing in here that can't say convert this from RPM to voltage. You can certainly do that. So that works okay. But just from a practical applications perspective, it's better to compare apples to apples. And this happens all the time. In Jude's PLC class, if you've done anything with analog inputs, you have a 4 to 20 milliamp loop or something like that that gives you the analog input. I'm not exactly sure what she uses, but let's say it's 4 to 20 milliamp. So your input signal is 4 to 20 milliamp. That could correspond to 0 to 1,000 PSI. Okay. But you're trying to control maybe a level in a tank. So I want this to be, I don't know, 10 feet ahead. So you're going to compare 1,000 PSI to 10 feet ahead. It doesn't work. So what you do is you divide this by, a number, and this become engineering units. Everything is a ratio between 0 and 1. So the speed or the water level or the pressure is all between a range of 0 and 1. So the input is between 0 and 1, and you can compare the output between 0 and 1. So you do everything in what are called engineering units, then you don't have to worry about any of this feedback stuff. It all happens to be on the same scale. So if you were to work in a PLC environment, you might actually see some scaling stuff that happens that converts that signal into a 0 to 1. That's how industrial folks like to do it. Even though we talk about PSI and milliamps, everything in a controller is done with engineering units. All right, so let's take a look at this example. So we have a controller in a plant. This is just a gain. It's a proportional only controller with unity feedback. So the question is, just by looking at it, what is the system type? Can you tell? How many poles at S equals 0? 2? 2? Any guesses? 2? Shall I restate it? If I plug in S equals 0, does the characteristic equation or the denominator go to 0? No. So there are no poles. at S equals 0. So there are no integrators. Remember, a pole at S equals 0 has to have an S out front here. This has an S to the 0. Yes, sir.
So system types itself.
Nope, it's the plant and the controller. But right now, the controller here is 1/1, right? So how many poles at S equals 0 in the controller? None, right? Same thing. So our open loop transfer function, let me erase some of this stuff so we can see. So our open loop transfer function is GC times GP, S plus 2 over S plus 1 times S plus 5. Now, what does the steady state error do to a step input? So without even doing the calculations, can you tell me for a type 0 system, what would be the steady state error? What was the previous calculations that we did? Remember, you have a unit step input that is running along, right? And this system has no integrators in it whatsoever. So is this system able to keep up with it at all? It can keep up, but it doesn't do very well, right? So you have a non-zero steady state error. So when you do your calculation for the proportional or the position constant, you take the limit as S approaches 0, GP, 2 divided by 5. Then you plug that into the ESS. We're going to assume that this is unit step, so we'll make that equal to 1. So 1 divided by 1 plus 2 over 5 is going to equal 5 over 7. Now, if we have a steady state error that's non-zero for any input that's greater, ramp or parabolic, you don't have to do the calculation. You know that that's infinity. You can check it if you want, but you know that those result, you're going to get a velocity constant equal to 0 and a steady state error equal to infinity, and the same thing with a parabolic input. So all you need to do is for the system type that you see, you do your one set of calculation, and then these, you just look it up in the table. Or you look it up in the slides that we talked about. What I mean by look it up is don't do the calculation. Just tell me KV and KA are 0, and ESS for both of those would be infinity. Right? Does that make sense? I only have to do one set of calculations. Now, if the controller was K, what changes? So instead of 1, what happens here? You got a K over here. You'd have a K up front, right? Here's a simulation, and you can do this really easily. So all you need to do is simulate, and we probably won't do this in lab until after the test, just because of the timing that works out. Because we're trying to get ready for a test, right? So we have a test a week from tomorrow. So tomorrow you'll do a study session with Conlon, and then we'll do another study session the Tuesday before the exam. And then we have the exam on Wednesday during lab. So we won't be able to do a lab on this for a bit. But when you do a lab, you build it exactly the same way that you would build any other Simulink model, but you're pulling out your error signal right here. That's all you need to do. Change anything that you've done in Simulink is just bring out the output signal so you can see it. So remember, the Simulink one is going to give you a time domain response, but it's going to give you the full time. It doesn't give you the steady state error until you see it reach quote unquote steady state. So if you were to run this in Simulink, here's your result, your steady state result. So you can see the blue is my input. I gave it a unit step. And then the red is the ESS. Oh, no, sorry, that's not ESS. That is the output. So this is the input. This is the output. The difference between these two, that's ESS. And you can see it's constant the entire time. It doesn't go away. It doesn't increase. It doesn't decrease. It stays constant. Now, if I go ahead and do my ramp input, so all I've done is toggle the switch from going from a step to a ramp. And you can see how my input signal, the blue line, continues to increase with time. But my output does increase, but you can see that gap is getting greater and greater and greater. And so this is only shown for 20 seconds. If you went to 200 seconds, that gap would be even further. So my steady state error approaches infinity. If time is allowed to go to infinity, my steady state error goes to infinity. All right, so now we're going to use this for design element, right? So the steady state error calculations are good, but again, we're engineers. We're trying to figure out how can we change things so that we can improve performance. So we would like to design a value of K or specify a value of K because we have some control over that value of K that results in a steady state error that's 10% or less, essentially. So the question is, I didn't ask you the input. What input should you consider that you'll have a 10% or less steady state error? Can you look just by looking at this input? I mean, looking at the block diagram. Can you tell? Well, can we rule any out? Can we rule any out if you're not sure? Can any of these be ruled out? Can I rule out any type of inputs that we know we're not going to get a 10% error? No way, no how. Step input, why can we rule a step input out? Why is it zero, the steady state error?
Type 1, I know it's not type 0.
So Drew is on the right approach. The first thing we do is look at the number of integrators at S equals 0. We see that this is S to the 1. So the system type is a type 1 system. And if you look at the rules for a system type, what we see is that for a step input for a system type 1, we know that ESS is going to be equal to 0. So if it's 10% or less, we can go with a type 1 system. I mean, sorry, we can go with a step input. For a ramp input, it's not going to be equal to 0. We know that it's going to have a fixed value. For a parabolic input, we know that it's going to be infinity. So there's nothing we can do to this system to make sure that we have 10% or less error unless we limit the inputs to step and ramp. So we don't have to do anything. We don't have to check anything for the step because we know it's 0. So that's always going to be less than 10%. So the type of input we should consider is a ramp input. Okay, makes sense? So here's that summary. You can take a look. So we have our system type, case of B. So that is where we're going to plug in our value. What do we need to do now? We're solving for case of B. Do we set that less than or equal to 10% or 0.1? We do not, because we want ESS less than 10%. And we can see ESS is essentially taking the case of B and inverting it. Okay. So we'll go ahead and we'll do our calculation with using our limit function. And what we end up with is 5K divided by 336. Now we flip that around or invert it, and we have 336 times A divided by 5K. And that needs to be less than 10%. Now, I said 10%, right? It's 10% of the input. So it'd be 0.1 times A, not 0.1, okay? Because we have an input, if we want it to be 500, we want the output to be within 10% of 500, not 10% of, of 1, essentially. So that's why we have to put the point A. So when you do that, your value of K needs to be 672 or greater, right? If K is 672 or greater, so if I increase K greater than 672, then that's going to be less than 0.1. Okay. So the limit here is K actually has to be greater than or equal to 672 for a ramp input to meet the 10% criteria. So when you're designing your system, you know that your proportional gain constant has to be at least 672. If it's less than 672, then your system's going to have more than a 10% error, which, what does that mean? Well, it depends on the process, right? If we talked about our adaptive cruise control and, if it's less than 10% error, maybe you're crashing into the back of a car. You don't know. So that would be somebody else would have to come up with what are the limits or what are the specifications that we need to come up with. You can just go ahead and figure out how to meet those specification requirements. Let's take a look at Simulink. So again, this is exactly the same. We're moving K out front here, but again, in MATLAB, this value of K, you can just enter it in the workspace. You can let K equal whatever value you want. But in Simulink, here's the representation. We're pulling out the error signal. And you can see, hard to see in here, but you can see that here is our input and here's our value. And if we run it at K equal to 672, hard to see, but you can see some oscillation. So it goes up to almost 0.2, but then it actually settles out to about 10%. Okay. And remember, we didn't say, so this is not a second order system response where we want the maximum percent overshoot to be less than 10%. We said we wanted this value to be 10% or less. So that would be a separate design criteria to say that error doesn't have to, usually you don't worry so much about the error. Usually you worry about the output signal. Is it going to ring? And if you look over here, it's hard to tell, but there is some ringing. Can you see? If you look really closely there, you can see the red line. So there is some ringing that happens at that value. It's just that you can't see it because we're zoomed in enough to see that it shoots up from there. So it does have a little bit of oscillation at low time, but in increased time, it goes away. All right, any questions on that? Because let's see if we can bring this up. Let me see if I can find this. Oh. I want the review manual. I want the FE electrical. What's the document called? See if we can find it in here. So normally, if you go on to the FE, you can go to this free reference handbook. I don't have an account number. So let me just try this and see if we can get it someplace. It used to be you can get this for free. let's see, where is it? Does this have it? Okay, so here's electrical and computer engineering. It might be hard to find. The one that's specific for electrical is quite easy to find. But this is the stuff that's in the manual. This is what they give you for a copy going into your test. I think it's electrical. It might be under mathematics. Functions, Bodie plots. What's that? Nope. No, we went through it at one point and it gives you the percentage of problems for each. But the reason why we cover this material is the control systems problems. If you know the material, are incredibly easy. They're so easy to do. It's very simple bonus points. Like this stuff right here, internet protocol. I mean, it might be easy problems, but you got a lot to memorize, right? And figure out what's going on. So I don't know. This is just a lot of material, but if you look at the control section, if I can ever find it. Let me try doing it this way. Sorry, I should have had this one up. All right, let's try it this way. I don't know if I'll be able to find it this way. First order control system model. So let's try it this way. There you go. Remember how I said system type? What's the T stand for? System type. Type 0, type 1, type 2. If the input is a unit step, and this is a unit step with a magnitude of 1 in the numerator, it's 1 over 1 plus k sub b. For a system type, for a unit step, type 0 for a unit step, you can see that's the steady state error. Then you can check for system type 2 or type 1, then you get no steady state error. And the problem is it doesn't show you how to calculate k sub b. I don't think. So the only problem with this is that this k sub b, it doesn't give you the formula to actually calculate k sub b. So you're just going to have to know it's the limit function as x approaches 0. You don't actually see that in here. So this is not a great one to show you how to do that. But as long as you know that it's k sub a, k sub b, k sub p, you can use this table to go ahead and calculate steady state error. And if you get a problem like this, it's as simple as look up this table. You just have to remember the limit function and go from here. So if you can't remember this, what you can do is say, well, I know k sub b. Oop, right on this. Let me annotate. So we know that k sub b is going to be some limit function as s approaches 0, s times my ES, right? We know that that's the equation. Or not S time, yeah, E of S. So the problem is, what is ES? And so this is where it gets harder. So ES is going to be equal to 1 over 1 plus KB, or it's just 1 over KB. We just don't know which is what, right? So the only way to determine what that is to check and see. We'll run this calculation and then see for a type 0 system, do you get the correct value. So actually, the only thing you need to remember is this, right? So here is case of B. So I guess let me back up. So for all you need to do, I thought I had closed it. All you need to do is remember one equation. Case of B is equal to the limit as S approaches 0, S times GC, GP, and if you have it, H. That's the only equation you need to know. Because case of B is my position constant. If I multiply S times case of B, then I end up with case of V. That becomes the limit as S approaches 0, S squared GC GP times H, because I'm just taking the derivative. So if I know what one of them is, then I can get the other two. So you only have to memorize that one equation, which really, if you can remember it from the final value theorem, you don't even need to remember it. You can actually just use that equation there. Okay? But that's how you would use this approach to pretty quickly, get a couple points on your FE, hopefully pretty easily. All right? So you can take a look and see about how to get there from here. So let's clear all these. Close that. Let's jump back to, where's the presentation? Where did you go? No, it's right here. I can't figure out how to bring it back. Is it here? Oh, I guess I can't bring it back from here. I don't know why. Okay, so if you have an undesirable, sometimes called a disturbance, you actually don't want the disturbance to be part of your output, but there's not much you can do, right? That's why it's called a disturbance. It's something that you can't control. There's something leaking into your system that causes a problem. So it's certainly not going to be coming in on our set point side. It comes in someplace in the plant, usually up front of the plant, downstream of the controller, because this is something in the physical plant that are causing some problems. So how do we solve this? We just do superposition. What is superposition again? Do you remember why we spent so much time in circuits 1 and 2 back when you were younglings or early in your electrical career, where we spent all these time learning these really crazy, why do we do KVL? Why do we do KCL? Why do we do superposition? Why do we do max power transfer? Why do we do this? Why do we do that? Well, the reason why we do it is because as you get to more advanced analysis, you can use those techniques to actually help you. So KVL and KCL, I mean, those are the fundamental ones to be able to do circuit analysis. So you kind of see where those make sense right off. But superposition, max power transfer, those are not as obvious, right? You spend a lot of time and you must have looked at Jude or John and said, why do I care about, why do I need to know this? Well, here's an example of being able to see where superposition is really helpful. So what is the concept of superposition? You can take any linearly independent system and you can find the output of such system by taking the inputs one at a time and turning all the other ones off and then calculating what the output is going to be and then adding them up at the end. So since this is a linearly independent system, that's the whole premise in control systems, at least undergrad control systems, we have to assume that the system is linear and independent. Otherwise, we can't do most of the work we've done for these past semester and a half. But we can go ahead and apply superposition. So our steady state error is going to be the combination of two factors. One is because we're trying to keep up with the set point or the reference signal. And the other one is because we have this disturbance. We're not trying to keep up with it. It's just that's what the value is going to be. So here's our first case where we have no disturbance, it's equal to 0. And then we calculate our steady state error from that. So we do our final value theorem and we go through that. The next one we're going to do is because of the disturbance. So here's the thing that's a little bit odd is when we turn off our input, this is 0, right? So when you add something that's plus to minus 0, essentially what you have is you can move your disturbance. You can move your disturbance, essentially, it's coming in over here, but now it just loops around this way. So it's still plus to minus here, right? Because the plus is coming in on the top. Okay. So the only thing is the order changes a little bit when your input, your reference signal is 0. So now we're going to subtract that because we have that negative, right? That comes back negative. So our ESS is going to be the reference input error minus the disturbance error. Now we take the final value theorem for that, and we end up with the same approach: S times RS, S times DC. This one changes a little bit because now you can see it's no longer unity quote unquote feedback. So this is the G over 1 plus GH, where that one is G and G sub C is H. So you got to be a little bit careful here. Notice that my simplification to just get the open loop transfer function changes a little bit, right? This is still going to be the open loop transfer function. This we have to use the closed loop transfer function to get back there. Okay. Oh, question?
Yeah, how do you get the ESS from due to RS and one due to ES?
You do them independently. You basically have to do this one here. This is ESS as a result of the R. So this is the superposition case. So we've turned off DSS. So now what I'm trying to do is get my steady state error from here. Okay. So this is no disturbance input. Then I've got to do the same approach to get here. But you'll notice this signal right here is my negative E of S, right? Because what comes back, this is the signal that comes back. So essentially what I'm doing is I go here, and then this signal comes back as a negative number. So this is negative E of S. Okay. That's why we have the negative ES over here. Let's erase that. Do you agree that this bottom block diagram on this page, that block diagram looks like what the model would look like if you had no input? You essentially set this equal to 0. Does that make sense? Okay. So now this is coming back. This is a 0. So 0 minus something. I can replace that by just making this coming back over here into my controller. I can multiply that by a -1. Right? Because this is a negative number. It's always going to be, it's 0 minus something. So my block back into the 0 I can throw that away because it's never changing. But what isn't changing is the fact that I've taken the negative of that number. So it's just the same thing as multiplying it by -1. So this is negative E of S, not positive, negative E of S. Yes, sir.
So if that's where the negative goes down from that first summation, then where does the negative come from? The figure out the bottom, when GC is coming back and added, yes, it's in the original, it's left added.
So this is negative ES. This is what it actually represents, but it still becomes plus minus here, right? So this is a negative. So instead of putting a -1 over here, I make it a negative number over there. That's correct. So let me see if I can show this on. Let me bring up whiteboard. Let's see if this makes sense. When we go for time, we get time. Okay, so does everybody agree that, let's just draw it all the way from scratch. So we have GC, this is our controller. This is our summing junction. This is plus plus, right? This is our disturbance. This is GP. This is fed back. This is plus to minus, right? This is a summer. And this is my error signal here, correct? This right here is 0 if I do superposition, okay? So what I'm saying is, let's redraw that. Still have my GC, still have my summing junction, still have my GP. But now, instead of the summing junction, because it's always going to be 0 minus something. So I'm not summing anything, right? It's always adding or subtracting a number to 0. So instead, let's just make that a -1 and bring that over here. Same thing, right? Because this, when this is 0, that means I'm subtracting that number. So I'm taking the negative of that number. I'm multiplying it by -1. So now I have this -1. I can either make this a -1 or make that a -1. That's all we're doing.
Error from basically
Yes.
that's why.
Yep, because it's still the error signal. Yeah, the steady state error is right here. It's the difference between what I want and what I got. It's not the difference between the disturbance and what I've got. It's the difference between what I want and what I got. And I want the reference. So that's why it's set up this way.
But then now, see.
What's that?
This plus goes, give it the negative. Give it the negative, give it the negative.
No, but this right here is the negative E of S. That comes back as a negative number. That's where this negative comes back right there, is because this is negative E of S.
So it's this one, right?
No, it's right. The reason why this is in this form here is because this is the standard feedback path. That's G over 1 plus GH. That's negative feedback. That's how we do the block diagram. But because this is negative E of S, we have to subtract it over here. It's not positive, it's negative, right? Because E of S, if you remember, is equal to the reference minus the feedback. And with a disturbance, this is 0 minus the feedback. So that's why it's the negative number. We get the negative from the feedback part. That's why that's a negative number. Okay. So that's the only thing that you have to add on it. Just have to add on the disturbance signal. And most of the time, because you don't know what a disturbance is, you've just got to take a guess. So is it going to be a step input or ramp input? You don't know. It all depends on the process. So somehow you have to become a master at being able to do that. So this is where the melding of control system engineering, a lot of it is done with electrical systems, but to actually do real control systems, you have to understand mechanical systems really well, or chemical or thermal systems really well, because these signals are coming in and you've got to be able to translate into what does that mean in terms of what's the output value going to be, or how does this affect what's going on? And so the disturbance normally would be maybe a leak, right? You got a pipe that's leaking water. So that's not what the system is supposed to do. But if there's a constant leak in a pipe, then you would model that as a disturbance. Okay. And then if you add in an H, again, now this is just a slight modification. So our error now is an actuating signal. So that's why we convert it back so that you can actually do comparison. So here's our R. Here's our transducer to convert that value to, the 4 to 20 milliamp, or the computer to convert it to a 4 to 20 milliamp, or a pneumatic signal or whatever. And then if the output you can't compare it to the input, you need a sensor to convert the pressure to a 4 to 20 milliamp signal. Then this would be called not the error, what you want between what you got. This would be the actuating signal error. Okay, so it's not the same, but you can convert that to a unity feedback doing some fancy math if you need to do that. But again, we probably won't need to do this because we'll just do everything in engineering units and it makes it easier. So if you have to do unity feedback where you've got these conversions going in here, your transducer has to be converted in your output. You just need to combine them. There's a typo here. Sorry about that. This is G1, G2. And then you have H1, G1 minus 1. And that is what your system becomes with standard unity feedback. So this here is GC, GP. So you would still do all the work, and then this just becomes your limit function. Here's an example. Calculate the steady state error due to a unit step. We see that G1 is equal to 1. H is equal to 1 over S plus 1. And G2 is equal to 100 over S plus 4. So our steady state error output over input. Here's our equivalent. Oops, of course I wrote it right over here. Here would be what our equivalent is going to look like in this case. So here's our G1, G2, etc. Here's those values, so I'll erase them now. Now we see them. Here's our value. It's 100 over S plus 4 divided by 100 times 100 over S plus 4 times the quantity. I won't state that again. It's all pretty self-explanatory. Here's our value. What type of system is this? Type 0 system because there are no integrators. So our steady state error to a unit step is going to be K sub P. Calculate K sub P first. It's 25. So our steady state error is 126. And then for a unit ramp, do I even need to calculate these? Just pull it from the table. If I go to here, we see that for our type 0 system, we see that the ramp input is going to give me a steady state error of infinity, which means that K sub B is going to be 0, and the same thing for the acceleration. So 0 and infinity, and I don't even need to calculate it because once you get to K, V is as infinity error, you're going to go ahead and get the value. Here's our simulation. You can do a step or a ramp. Here's the step input, and you can see that it does settle out. Hard to see, but there's a slight difference between the red and the blue. And then here's the actual error signal, the RT minus there. You can actually see what the difference is in steady state. So the red and the blue are the actual signals. The green line shows you what the actual value is. Now we go ahead and do the next case, which is our ramp input. Oh, no, this is just zoomed in, sorry. So you can see the oscillations, we're zoomed way in, and then you can see this is 1/26 away from, so 1 over 26 is about 0.03, blah, 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 etc. This right here is 1/26. That's the difference. Okay. And that's it for steady state errors. Questions on steady state errors and all that stuff? I know everybody's having a hard time getting back up to speed after break, but
How did you do the 1 bar go inside the
say that again.
field picture?
Yeah.
So the oscilloscope cut 1 feeding back bar, going to the oscilloscope,
Do the oscilloscope and simulate.
but then no, like the 1 bar taking 2.
This right here.
No, it's to the left here. So oscilloscope feed like bar.
Oh, the bus.
Yeah.
That's an option that you can do in Simulink. In Simulink, you can actually, let me see if I can bring it up here really quickly. I hate running Simulink because it uses so much memory. But I believe It's the, it might be the standard one, but if we hold on while it brings it up. Let's just do blank. Okay, see, like I said, this is why I hate running simulink, because it uses a lot of resources to run. And I'm sure you're all dying to watch this computer run when you could be studying and all that stuff, but I didn't expect, had I known the question, I could have brought it up, but earlier. But there's a block, and it's basically just a common node. You can actually also do a summation block if you want, but this one just shows it more obviously. But you can do a summing junction, you can do that as well. So, yep, you can sub signals and you can do it that way. Sometimes it's better to keep them separate, but this one just, you know, the thing about,
So the output twice to give you two graphs.
well, but oh, no, it doesn't. It gives me one graph. One's the error signal and one is a combination of the two, right?
What gives you one graph?
Right.
Summation one.
It would just have, it would have the one, yes. Yep.
So you one graph to nine.
Yes. So that's why this is the error signal that gives you here. And over here, it gives you the input and the output, it gives you the two. Yep.
That's just called bus.
I think it's a bus. So, let's see if we've launched yet. Not yet. Let me hide this. So it's not under common ones. I think it's under continuous. No.
Just like awesome.
How about ports? What's that?
But just search.
But I can't remember what that's called. Is it called a bus? Electrically, we call it a bus. We can do it really quickly and see. So there's maybe it's the multiplexing of signals. So is it here? Takes the two signals in and then puts it in one. So I think it would be this one. It's like a multiplexer. So this says it's bus creator, but I wonder if it's in, here we go. So under commonly used blocks. Actually, I think the better one would be a multiplexer. Mux is a mux multiplexer where you just take the two signals and you combine them into one. So you can have the two, you can see the two waveforms. So it's under commonly used blocks.
Or the paths.
No. I think you would use a multiplexer. That's what I believe. That looks like here, yep. So it's just a multiplexer. If you did control systems, multiplexing and demultiplexing, that's just an old communications term. MUX. That's the abbreviation for a multiplexer. We can drop it in and we can see. So let's drag it over. It's not the most efficient one, as you can tell. And then you can double click it. And you can get information. You can also do help. Here's our connection, but you can do the help on it, but yeah, it's just this one. All right, questions on steady state errors? No. Nope. If you look for our next Tuesday's class, I've already posted the exam review. Because I have to do the homework, and if I assign the homework today, the earliest it would be due would be Tuesday, right before the test, which doesn't give you a whole heck of a lot of time to study. So we'll move that off into the next material. All right, any questions? All right, no questions. Have a great day. And I'll see you all. Hopefully I'll be here tomorrow. I do have a sick kid at home with conjunctivitis, so I don't know if you know what that is, but that's goop in your eyes, basically. So he got pulled out of school yesterday, and he's out of school today. My wife is covering, but tomorrow, if I can't come to campus, I'll still be around, but I've got sick kid duty, so hopefully that won't mess up too much with tomorrow, but I apologize in advance if you don't see me tomorrow, so that will not work well. It just depends on how his eyeballs are doing, so. Okay, have a great day, and we'll see you all hopefully tomorrow. Take care, everyone.